In this video, I'm going to go through the key ideas in quantum. These are all the things you need to know to master the topic of quantum. This is Guerrilla Physics. Other channels, they teach you the content, but I'm going to teach you how to get the A star. Biggest idea in quantum is that in atoms, there are only fixed, discrete energy level changes that are possible. When atoms absorb photons, they move up the energy levels. They can only move up those fixed, discrete energy level changes, so they can only absorb certain energies of photon, so certain frequencies of light. When those electrons fall down the energy levels, they only can fall down certain fixed, discrete energy level changes, so they can only emit certain photons of light. And those photon energies are the same whether they're being absorbed or emitted, so therefore they absorb the same frequencies as they emit. I'm going to teach you how to describe quantum behaviors, and I'm going to teach you how to make the calculations in it as well.
In fact, quantum physics is really easy to understand, or at least it is at A level. Let's start establishing a few things. Quantum is about discrete energies, and it's about the emission and absorption of light from atoms. So look at this match head. How many different colors can you see? You can probably see a few, but you certainly can't see a continuous spectrum. Now the hottest parts of the flame are the blue parts, and the coolest parts are the yellowy or the red part. But you can't see any green in that. Let's just say we can see some blue, and we can see some orange, and we can see some red. We cannot see a continuous change. So this is evidence for light coming in discrete packets or quantums. Light comes in discrete packets certain discrete colors, only a few colors. And it's called a photon because it's a wave particle. Photo means light, and anything ending on is a particle. So it's really not scary at all. It's just our best description of where light comes from and where it goes when it's absorbed by atoms. So you will be familiar with the Bohr model, which is this idea that we've got protons and neutrons in the nucleus, and we've got electrons orbiting in kind of energy levels. Now in chemistry they call them shells, but actually this is where we need to divorce the idea of a shell in chemistry from an energy level in physics. And luckily you don't need to worry about shells and orbitals and things like that in physics at A level, but you do need to worry about the energy levels. And in fact we're going to really simplify things. But I've drawn this helium here with very, very simple energy levels because I want you to get the idea. This is an idea that you're reasonably familiar with already. The idea that the electrons have different properties depending on their position within the atom. Is actually about their potential energy within the atom. It's not the case though that the least energy is necessarily the furthest away or the closest. It's about some property of their orbit, how much energy they have in that orbit. It's not necessarily how far away or close they are. And it's not the exact same thing as shells in chemistry. Let's focus at first on understanding a key idea, which is how light comes in and out of atoms. And that's all I want you to get from this slide. When a photon is absorbed, when the light is absorbed, an electron moves up the energy levels. It takes the energy from the photon and it moves up the energy levels. It has more energy. When light is emitted, then the electron moves down the energy levels. So a photon being emitted corresponds to an energy level change where the electron moves down, it gives out energy, it has less energy afterwards. We call this when the electron goes up an energy level, we call that excitation, and when it comes down the energy level, we call that de-excitation. So why then are there so few colors when the match was lit? Why is there certain discrete colors? Well, there isn't an unlimited number of options in that situation. There's only specific energy levels, so they can only have certain energy level changes, so the light can only have certain colors. The photon's color is governed by their frequency, and their frequency is governed by their energy. So here's two really, really simple elements, the two simplest elements. And normally at A level, we'll talk about simple elements because it just simplifies the math. Here's the emission spectra from hydrogen and helium. These are the colors that are given out by those two elements when they burn or when they fluoresce, but basically when the electrons de-excite, when the electrons come down energy levels. So when the electrons de-excite, they give out these specific colors. They give out a little bit more orange than they do these purple ones, and that's why that band is slightly thicker, but they only give out these certain discrete colors, these fixed frequencies, these fixed wavelengths, if you like, of light. And also, which ones have the highest energy? I'm hoping you won't struggle with that idea from your ideas about the electromagnetic spectrum you should already have from GCSE, which is that the purple end is a higher energy end. The blue end of the spectrum is higher energy than the red end of the spectrum. So these photons have actually higher energies. Therefore, they correspond to higher energy level changes. Let's just really establish this key idea of quantum. The photon energy is proportional to the frequency, and we have to thank Max Planck for this. Essentially, the higher the energy, the higher the frequency of a photon, of a wave particle of light. Wave particle duality is an idea that we came across in previous video and is a central idea in quantum, which is that things show both waves and particle behavior. Light is a photon, it's a wave particle. So Max Planck put forward the Planck postulate, which essentially quantizes light, which essentially gives us the photon. The two parts of the Planck postulate are that the energy of a photon is proportional to its frequency. And here's this key equation, E equals hf. The energy of a photon is equal to the Planck constant multiplied by its frequency. And secondly, that the photon energy can only be emitted and absorbed in multiples of some fixed fundamental unit of energy, some fixed discrete quanta. That's where that word comes from. All of quantum physics is about these fundamental units of energies that we can't change, so we only get multiples of. So let's do some practice to make sure you know exactly how you're to use that equation, E equals hf. Firstly, we're going to use Planck's constant as 6.63 times 10 to the minus 34 joules seconds. And so you can see that as just a bit of a conversion factor between either frequency and energy, or even wavelength and energy, which we're going to use today as well. It's a number which is given on the formula sheet of any A level, so you don't need to memorize it, but you will remember it because you'll be using it so many times. Here's the first one then. Calculate the energy of a photon of blue light, which has a frequency of 6.79 times 10 to the 14 hertz. So we start in the same way we do every single calculation. We just write out our equation, everything we know about the question, checking that that is indeed in SI units. Now substitute the values in. 4.50 times 10 to the minus 19 joules. So that is a really simple one. That might even just be for 1 mark in an A-level paper. Slightly more complicated though. What if they've given you a wavelength? Well, the first thing you're going to need to do in this case is to actually convert between a frequency and a wavelength. We're still using this. We're still going to do E equals hf, our equation for the energy of a photon. So we need to use C as f lambda because we've been given a wavelength and we need to use a frequency. So we need to work out frequency is C over lambda, which is 3 times 10 to the 8. That's just something you will memorize. That's the speed of light in a vacuum, over the wavelength, which is 332 times 10 to the minus 9 meters. And that's just a conversion straight away. I see nano and I write times 10 to the minus 9. So 5.64 times 10 to the 14. Now I'm going to leave that in my calculator because I would like all the significant figures where possible. But I'm going to do Planck's constant 6.63 times 10 to the minus 34 multiplied by that frequency gives me 3.74 times 10 to the minus 19 joules. So that's a slightly more complex one because you've had to do 2 steps, so probably 2 marks for that one. Now you will probably have recognized there is a little bit of a shortcut for that, which is that actually I can substitute this value in here instead of the frequency. So there is one more equation that often isn't given, but actually is a very useful shortcut. If you're given a wavelength, you can work directly into the energy in joules. So all I've done here is substitute this expression for frequency into my Planck's constant equation there, my energy of a photon equation there. Okay, last one then, and this is just working backwards. Calculate the wavelength. So I'm actually going to use this equation this time where they've given me an energy. So the energy they've given me is 2.95 times 10 to the minus 19 joules. And I am just going to substitute that value in and rearrange for lambda, or I'm going to rearrange for lambda first actually. And that does make sense. 6.74 times 10 to the minus 7 meters. We've got 674 nanometers essentially. So that is just how we use that equation E equals hf. If we were given energy, a frequency, or a wavelength, we can just convert between them. I'll put a link to this simulation as well in the description because it's a really good one to play about with and get your idea of the energy levels in a hydrogen atom and what that means. But really what I want you to take from this is that the energy is proportional to its frequency. If I were to plot a graph of the energy of a photon versus the frequency of the photons, the gradient would be h, the Planck constant. and that photons can only be absorbed or emitted in these fundamental frequencies. So I've got the PhET simulation here, absolutely amazing simulation, this one. You can work through all of the different models of the atom. We're just going to stick with the Bohr model just for now to help us understand exactly what's happening when photons, these are the photons of light, interact with the electrons in an atom. So you see, sometimes you will see the electron raising up the energy levels, and that is when it is absorbing a photon. I'm going to slow it down a little bit so hopefully you can see an individual event happening. And notice that it will ignore, it won't interact with a lot of the frequencies of light, they'll just go straight past it. And that's because there is no energy level change which corresponds to that frequency. Now hopefully you saw that it absorbed a ultraviolet and it raised right the way up to the highest energy level. And then as it fell down, it emitted a specific discrete frequency of light, a specific photon of light. Then it fell down again and it emitted a different one. But because there's only certain options, it's only going to emit or indeed absorb those corresponding energies of photons corresponding to those energy level changes. One of the nice things about the simulation is that I can actually show you what's called a spectrometer, which is going to display all of the different frequencies of light which are emitted by this atom. So every single time, I'm speeding it up now, every single time a photon is emitted as an electron de-excites, which is falling down, you can see it registers one photon down on the spectrometer down here. So I'm starting to see these discrete bands, these discrete colors, which are like the emission spectrums that you saw on the slides that I presented to you. Gradually that's going to build up. You can see for hydrogen, we have these 4 discrete bands in the visible spectrum, these 2 in the UV, and these in the IR range as well. And as we go, we'll see we're emitting more regularly, we're emitting these or these more often, but the purple ones less often, but never somewhere between this purple and this blue. Never somewhere between this blue and this cyan. Never somewhere between this blue and this red. So only emitting these quantized values, these fixed frequencies of light, which corresponds to those fixed energy level changes. I'm going to slow it right down again. I'm going to show you how we simplify this diagram. Right at the start, I told you this was not a very accurate picture to have these circular orbitals. So I'm going to show you this energy level diagram. So this is a much more simple picture. We have the electron currently is on the ground state, it's on n equals 1. It's got the lowest possible energy it can have in the atom. Now it's been excited. It absorbed a photon and it's raised right the way up to n3. Now it's fallen down, it's de-excited, and it has emitted a photon. So if you just watch this, as it absorbs photons, the electron is raised up the energy levels. So these simple energy levels just here. And as it de-excites, as it emits a photon, it falls down the energy levels. And the photon it emits corresponds to that energy level change. So the first time you see that electron energy level diagram, it looks quite complicated, but in fact, it's a simplified picture. I'm just going to speed that up so you can watch that just a little bit. Excitation and de-excitation are shown there. Just for your information, we've also talked about the wave-particle duality of electrons, and this simulation can also show this wave-particle nature of the electron. It's the same idea, it's just that when the electrons show wave behaviors, they have frequencies and wavelengths which correspond to their energy levels as well. We can also talk about Schrodinger's idea about the probability clouds of electrons, and they have different probabilities of being found anywhere in these locations that are shown by the blue areas on the diagram there. But this is not for A-level physics just now. We only need to explain things, in this case in quantum, in terms of the Bohr model. And that the energy can only be absorbed and emitted in these fixed discrete quanta, these fixed frequencies, these fixed energies. So notice that the atom of the hydrogen only absorbs and only emits these fixed frequencies of light. Now here's the pro tip when we come on to explaining this later. When you're discussing this, discuss discrete energy level changes. There are only certain fixed energy level changes that are possible. When it absorbs some light, there's a fixed set of options. There are fixed energy level changes which are possible that the electron can move up. So it's only going to absorb those corresponding frequencies, those frequencies corresponding to the energy level changes which are possible, the fixed or the discrete energy level changes which are possible. When the electrons de-excite, when the electrons come down the energy levels, there are only certain fixed discrete energy level changes which are possible, and that corresponds to all of the different possible energies of photons, which correspond to the different possible frequencies of photons. We'll come back to this idea when we talk about how to describe quantum behavior in the later part of this video. So great simulation, check that out, that'll be in the description as well. Thank you very much to PhET for their amazing simulations. Now we're talking about diagrams, remembering we don't bother drawing them as these circles, so we just draw these as these simplified diagrams, the lowest energy level being at the bottom, the highest energy being at the top. When an electron absorbs a photon, it is excited, it's raised up the energy level. When it de-excites, it emits a photon. And just note for now that this is a higher energy because it's a higher energy level change, so it's a higher frequency photon being emitted. The next new idea is that we're dealing with really small values of energy when we're talking about individual electrons. So using joules is not a very sensible unit to use. Calculations with energy in joules gives us really small values. So we've come up with a non-SI unit, which we can use to represent values on these energy levels, which is just much more straightforward. It gives us much more straightforward numbers to work with when we're dealing with these very small values. It's called the electron volt, and 1 electron volt is defined as the kinetic energy given to an electron if it's accelerated through a 1 volt field. So we aren't talking about particle acceleration yet, although we will do later when we talk about electric fields, but just that is the definition of an electron volt. Essentially, if we were to have an electron here and we had a potential difference of 1 volt, so 0 volts there and 1 volt there, and we allowed that to be accelerated because it'd be accelerated towards this positive charge over here, then this electron, as it reached this point, would have a kinetic energy equal to 1 electron volt. Well, what does that mean though? Well, let's think about our equation for potential difference. Potential difference is energy per unit charge. Rearrange that for energy. Energy is charge multiplied by potential difference equals QV, and the charge on an electron is E. So 1 electron volt is equal to the charge on an electron 1.6 times 10 to the minus 19 coulombs multiplied by 1 volt. So 1 electron volt is 1.6 times 10 to the minus 19 joules. You're just multiplying by 1 there. That is the definition of electron volt. So again, this is just another conversion factor that we use when we're dealing with very small values of energy, as we are currently when we're talking about individual electrons. And we'll use that again a lot when we do particle physics. So here's 2 questions where we're going to use electron volts as they are now on the energy levels. We've used actual electron volts here, and we're going to calculate the frequency of the emitted light. Before we go on, I just want to talk about the idea of having 0 at the top and having our lowest energy being minus 13.6 electron volts, and having our lower energies being negative values. Now, it's a bit of an odd idea. We're only ever, in this case, interested in energy level changes. So all we're doing is we're saying that when an electron is at the very highest value that it can have within that atom, it has 0 electron volts of kinetic energy, if you like. Now, we need to give the electron some energy if we wanted to get it up to that value. So we can talk about that as having minus this value of energy. It's not negative energy, it's a negative energy change. Now, the way to think about that is you've just moved where you're measuring 0 from. The best explanation I've ever heard of this is just think about measuring people's heights from the ceiling rather than from the ground. Now, actually, the shortest person would still have the lowest number because they would be furthest from the ceiling. So these energies are all relative to the valence band. They're all relative to the electron, which is at the highest possible energy level. So this is still an application of our equation for the energy of a photon, E equals hf, but our E is actually a change in energy between 2 levels. So our first thing to do is to work out our delta E. That is minus 13.6 minus 3.4 electron volts, 10.2. Now the change in energy for that electron is 10.2 electron volts. Before we use that in any calculation, just as every single time ever, we need to convert that into SI units. here's my simple rule to follow whenever you're converting between non-SI and SI units. If you've got a non-SI unit, then you use that unit a little bit like it's a formula. So to turn that into energy in joules, I'm going to do 10.2 times by the charge on an electron, 1.6 times 10 to the minus 19. Again, that value is in the equation sheet, so you don't need to worry about remembering that. Multiplied by 1 volt. Now, I'm going to do that just for the sake of argument in this case, but I won't do it again in the next example because we don't need to multiply by 1. But that will give me a value of energy in joules. 1.632 times 10 to the minus 18. That makes sense because it's roughly 10 times the value of 1 electron volt in joules. So now this energy is the one that I need to use here to work out the frequency. Rearrange the full frequency gives me E over H. 2.46 times 10 to the 15. 2.46 times 10 to the 15 hertz. And that makes sense. That is slightly higher than a visible light frequency. That is an ultraviolet frequency. So that makes sense. That's quite a large gap. That's quite a large jump up the energy level changes. So what about a larger change? And this time we're emitting light. But the question only asks us to calculate the frequency of the emitted light. So all I'm interested in is that change. And that change doesn't matter whether it's positive or negative. We can't have a negative frequency. We can't have a negative energy of a photon. We can have a negative change in energy. But in these questions, we're only ever worried about the magnitude of that energy level change. So once more, I'm just working out my frequency using my energy of a photon equation, E equals HF. First of all, I need to work out my energy level change. So this time I've gone from 0.85 down to 13.6. I only need to work out the difference between those two numbers. It really doesn't matter about the signs in this case. 12.75 electron volts. I've got non-SI and I need SI before I do any calculations. So I'm just going to multiply by 1.6 times 10 to the minus 19, which is the conversion factor between electron volts and joules. Now I can use my equation to work out the frequency. 3.08 times 10 to the 15 hertz. So that is emitting a frequency which is in the ultraviolet band. This is a really tricky concept conceptually. It's stuff that you're not really used to from GCSE. It's stuff that's kind of new in A-level. So don't be worried about really understanding it and getting it first time. It's tricky, come back to it. But I suggest whenever you're asked anything like this that you kind of memorize what it says in mark schemes, because then your understanding will develop later and you'll have that memory and you'll be able to at least get the marks in it. You'll be able to get the marks when you spot a command word that says describe quantum and you know it's about absorption and emission of light. Well, okay, here's the stuff lifted directly from mark schemes. Just make sure you get the terms that are in bold in this here. So you talk about the electrons are involved and they're moving to higher energy levels when they're absorbing, or you can say that the electrons are excited. Then the point is they move back down to a lower energy level. They move down to the ground state, if you like, and energy is given out in the form of a photon. So you're getting that keyword photon in there. And here's the important bit. The energy levels are discrete. Only fixed, only certain energy levels are possible. So only certain energy level changes are possible. So here they're saying the point is HF is equal to the difference between the energy levels, or HC over lambda is equal to the difference between the energy levels. There's only a limited number of energy differences that are possible. So there's only set frequencies or set wavelengths that are possible. And different elements have different energy levels, so they give out different frequencies of light. So you make sure that you get in those key terms. It's all about this idea of discrete energy level changes are possible. I would memorize exactly that term. Discrete energy level changes are possible, and you get that into your answer. So what about ionization? So ionization is when the electron is given so much energy that it actually leaves the atom. So let's say a gamma photon or a very high frequency ultraviolet or an X-ray will give enough energy to actually escape the atom. There's no energy level that's actually high enough within the atom for that electron to remain in the atom. So it leaves the atom. The atom is left ionized. So if you're asked to describe ionization, or maybe you're asked to describe the photoelectric effect, which is the same kind of idea, where we've given an electron enough energy to leave the atom, we're talking about individual photons interacting with individual electrons, and we're talking about the energy of those photons being equal to hf. So in the photoelectric effect, we're talking about there being so much energy in the photon that the electrons actually left the atom. So therefore, we're talking about photons which must have a frequency greater than a minimum frequency for that electron to leave the atom, to be emitted from the atom. Now, you can either talk about frequency and threshold frequency, that's a minimum frequency as a threshold frequency, or you can talk about the photon energy, but don't mix and match. You wouldn't get this mark if you said frequency greater than the work function, because the work function is the energy, the minimum energy. Now, they are related by this equation HF, but they aren't the same thing. So just be really careful around that language. Either say the frequency has to be greater than a threshold frequency, or say the energy must be greater than a work function, or say both, but don't mix and match them up. Say that in full. Now, what happens in the photoelectric effect is that light with a greater intensity supplies more photons per second, so more electrons are released, okay? So there's a higher rate of electrons being released. That's that per second bit. More photons per second, more electrons per second, causing a greater current. And the key observation in the photoelectric effect is that for greater intensities of light, which is below the threshold frequencies, you don't get any released photoelectrons, you don't get any emitted electrons from the surface. So that is the key bit of evidence for this whole idea that light is both a wave and a particle. And this is just relating back to this equation, Einstein's photoelectric equation, which is the energy in a photon is equal to the work function plus the energy that the electron has left, the photoelectron has left in the form of kinetic energy when it's emitted from the surface.
I hope that was useful. If it was, then just comment boom in the comments box below. And don't forget to subscribe to Gorilla Physics. I'm going to teach you how to get the A star. Check out gorillaphysics.com for all of my videos organized by topic.